In 4.3, we'll be doing the diagnostics on the least squares regression line. In a nutshell, it just means how good is the least squares regression line, all right? So it says we want to measure how well our model really explains the relationship. So how much does it explain? Could we improve it? Could we, make it better? If we have a value of x and we use our model to predict y, how accurate are we really? Okay. So the coefficient of determination, guys, you want to realize that's our last little guy from our calculator. So on Wednesday last week, when we did our calculator cheat sheet, we were given y equals ax plus b, we were given a and b, and then we were given an r squared and an r. And we used everything but r squared, okay? And the r squared is the coefficient of determination. What it is, it measures the percentage of total variation in the response variable, so that's your y variable, that's explained by the least squares regression line. Basically, guys, it gives your line a grade, okay? If you got 82% of your coefficient of determination, that's a pretty good line, okay? That line does a decent job of explaining. So this back cap here, guys, is just kind of a quick review. Since we're squaring r, and guys, it's literally r squared. So your calculator doesn't really need to give us r squared. It gives us r, we should be able to square it. But do you guys remember the two values that r ranged from Wednesday? What was the lowest r could be? -1. What was the highest it could be? +1, right? If you square that, what happens to all your negatives? They become positive, right? So now what's your lower end? What's the lowest you can go? 0, okay? So r squared, the lowest it can go is 0, and the highest it can go is +1. Again, think of it kind of as a grade, a 0% or 100%. So values of r squared with close to 0 indicate very little explanatory power, meaning that's not a good line. That's a pretty crappy line. We can do better than that, okay? A value of r squared close to +1 is about 100% explained, and there's very much explanatory power there. That's rare, okay? If you did that with your algebra classes where you were given perfect lines, your r would be 1 and your r squared would be 1 because there's no variation, it's a straight line. But in real life data with our stats, it's going to be like 90 something, okay? It'll rarely be 100. All right, this is just showing you that the coefficient of determination is literally r squared. They use capital R. Guys, I'm not picky because your calculator uses little r and it is little r squared. So whether you use capital R squared or little r squared when you're denoting your coefficient of determination, I don't care. Always use technology. It's going to be on our calculator. All of our computations on chapter 4 are going to be done on our calculator, okay? So don't think we have to go looking for some crazy formula there. And then last but not least, this is just kind of a reminder of what happens when you square decimals. So it's a little backwards, okay? Say we have a very strong relationship. Let's say we have like 0.9. That's a good relationship. If r was 0.9, that's really good, right? But what happens when you square 0.9? What does it become? What's 9 squared? 81. So guess what 0.9 comes? 0.81. All right, so what happens, guys, is when you square decimals, when you square numbers smaller than 1, they actually get smaller. So kind of keep that in mind. So if you get an r squared of 0.81, you're like, oh, that's not the best, that's not the best strength. Actually, it is, because 9 is really strong. Let's go in the middle here. Let's go at like 0.6. That's kind of that borderline. We're starting getting close to our critical value. It's not that great. What happens when you square 0.6? What do you get? 0.36. Look how low that drops. And last but not least, let's just say we're barely there. We're at like 0.1. What happens if we square 0.1? We get 0.01. These do not need to be memorized. They're just kind of there to point out what happens when you square decimals, okay? I think you're going to find a lot of our stuff's either very, very strong or very, very weak. And so it's going to be kind of up here in the 0.9s or here in the 0.6s. There's not going to be anything really major, okay? The last little note here says, as far as our course goes, you will use your graphing calculator to find the least squares regression line. So remember, that's y hat equals ax plus b, the correlation coefficient r, and the coefficient of determination r squared, okay? So the only kind of computing you have to do will be, you'll have to be able to find the residuals, so the observed minus predicted, and then you'll also have to be able to find those predicted scores. That's when you plug it into your line. So last but not least, oh my goodness, last time we have to see this data, let's go ahead and figure out what r squared is for our golf club data. So go ahead and get out your calculator. Some of you might have not done a single thing since Wednesday, but you had to do that worksheet at the end. So I bet all of us have to re-put this in our calculator one last time. So let's just kind of do a reminder, or for those that had to leave early, what you do is this is list 1, this is list 2. So you go to Stat, Edit, clear out your list by hitting delete, not clear, right? No, clear, not delete. Put your club speeds in order just like that in list 1. Put your distances in order just like that in list 2. And then remember, it's Stat Calc 4 for Chapter 4. Stat Calc 4 for Chapter 4. From that, you're going to get everything we've done so far, okay? You're going to get our R value of 9387 that we talked about on Wednesday. You're going to get our least squares regression line, that 3.2 for our A, that negative 55.8 for our B. But the last thing we want is R squared. So you should get to 4 decimals. Let's see, I got to catch up with you guys. To 4 decimals, r squared, let's make sure it's on there. R squared, did you guys get 0.8811? Yeah. Does that look right? Okay. And remember what we talked about. We had an R value of 90 something. So when we square it, we should get 80 something. This makes sense. This is still a really strong line. Okay. What does it mean in a nutshell? It means about 88% of our data follows the line. There's about 12% that's off for some reason. Maybe because humans are humans and they're not perfect, so they're not swinging the club exactly the same every time. Or like I said, somebody blew a blowhorn, so then the swing's off, whatever it may be. So this is what I'm kind of looking for, basically word for word. So I'm going to put it in quotes, because if you quote it, this is what I'm going to look for on the test, okay? In quotes, 88.11%. So that's going to change. I'm underlining that because that's our R squared, so that will change. 88.11% of the total variation in distance is explained by the least squares regression line. .1% of the total variation in distance, so that's always going to be your y variable, is explained by the least squares regression line. And some of you might think, oh my gosh, this test, I'm already going to have so much. How am I going to remember this line? If you flip back and look at the definition of coefficient of determination, this is just the coefficient of determination definition. It's the percentage of the total variation in your y variable that's explained by the least squares regression line. And that's on your formula sheet, okay? So the definition of coefficient of determination is on your formula sheet. All you have to do is change the percentage to the actual percentage. And the y variable, I think in the definition it says response variable, to the actual y variable. And again, if this was fake data, if it was a perfect line, we'd have 100% it's explained by the least squares regression line because every dot falls on that line. But since our data was real, this golf swing was not perfect every time, the wind was not perfect every time, we didn't have a perfect line. We are off here and there, okay?